Here we are once again for another Physics 105A video lecture. This is Physics 105A video lecture 7. And start with a couple announcements again. So first of all, any homework from this lecture would be due after the spring break. This is the last lecture before spring break. And what else do I have here? There was a little error, probably not the only one, in the 6th lecture, where somewhere towards the beginning I was taking the divergence of the gradient, and I had this expression there. You'll find it with an extra little 2 up here somewhere. Okay, that was just the way I ended up writing it down. Everything downstream from that was correct again. But yeah, you can correct that, and where there's if you happen to copy it down that way, you possibly caught the thing right away. There's only that 2 right there. And when you add them up, I equals 1, 2, and 3, it turned into an r squared and canceled the r squared from down there, leaving just the f double prime of r expression. Good, so you can make that correction. Then what we're doing today, the 2-body problem. That's what I left off with last time. 2 bodies in measureless space interacting via some central force, namely towards each other, away from each other. And from there, we'll make it back to the formalism that we had before, the central force formalism. And then if we get that far, we'll set up the actual Kepler problem, work our way through there a bit. The actual Kepler problem is when you have the Newton's law of universal gravitation, 1 over r potential. You bring that into the formalism and then take it all the way through. Okay, so let's get started. Okay, what we have when we're talking about just 2 bodies is, I'm going to draw this a little larger than last time. And we've got M1 and M2 out in space, 2-point masses. And they have a position, so you've got some arbitrary origin, you've got their 2 vectors. Draw the vector first, then the mass, okay. M1 and M2, and these are the vectors R1 and R2. Okay. And if we just had that, in fact, let's go ahead and do this really thoroughly. So we've got 2 bodies out in space, 2-body problem. Then what would Newton's law be? We would have M1 R1 second derivative. Mass times acceleration would be the force of particle 2 on particle 1. I could express it that way. Right? It's being acted on by the other force. And we would have M sub 2 R sub 2 second derivative is equal to the force that 1 exerts on 2. But by Newton's 3rd law, they're equal and opposite, so minus F. And you know, I'm just going to erase these subscripts. You got them in your notes. Now we can erase them. Yeah, so Newton's 2nd law gives this form. Newton's 3rd law tells us that these 2 forces are equal and opposite. Okay, so then what would we do? This is actually too much to solve. Okay. In space, we have 6 quantities now, 2 3-component vectors. But there is an interesting strategy here. What we do is we take this equation, multiply it by M2, and this equation, multiply it by M1. So what we're going to get is M2, and here I'll give myself a little more space. I want this to fit. Okay, so we're going to have M2, M1, R1, second derivative is equal to M2F and we're going to have m1, m2, r2 acceleration is equal to minus m1 f. And what we've gained is the following, really interesting little trick here. I'm going to subtract the second equation from the first, and on the left side I'll just have m1, m2, that's common. R1 second derivative minus R2 second derivative equals m1 plus m2 times f. And now this thing here is going to be R double dot. Now let's go back to our drawing and define this vector R. They've had that on the last notes, right? They've ended up with that. Definitely draw attention to it now. So this is the difference vector, R1 minus R2. Right, as defined, it points at M1, points at R1, R1 minus R2. Okay, so that's that difference vector. And now, since I need a little more room, I'm going to erase these. You have Newton's law for those individual particles. Let's put this one back up at the top of the board. M1, M2 R is equal to, oh, and you know, I'll just take this step here, M1 plus M2. So I've divided, let's put parentheses, okay, let's be serious about this. R double dot is equal to, okay, I've divided that out, so that is my force. But now, what about that force? Well, it's a force between these two particles, and we're talking central forces. So in fact, that F, vector F here, is of the form F of R. Okay, what a coincidence, what a circumstance. Okay, this, by the way, had, yeah. That's right. Okay, I was wondering if I lost the minus sign. I did not lose the minus sign. Okay, so we've got this, and then we have the central force. Why? Because this force was the interaction force between these two particles, and it depends on the separation distance. And the magnitude of this R is the magnitude of that difference right there. Okay, so there we have it. And this interesting quantity is referred to, I'm just going to call it M equals product of the masses divided by their sum, and that's what's called the reduced mass. We'll say a couple words about that. That's what's called the reduced mass. And you'll see I can now write mR second derivative. So I've now made contact with our original central force discussion. So we can, so to speak, take it from here. So let's say a couple words about the reduced mass first of all. What is the meaning of that? In the case, so I'll put a note here for the reduced mass. You can say, well, that's just formal. It has the definition of mass and it involves both masses. Suppose we have a large mass. Let's say M2 is much greater than M1. So we've got a large mass and we've got a small one. And we call this one M2, M1. So what I just want to do is evaluate the reduced mass for those circumstances. Okay, I'll use this part of the board and then I'll erase it. But so now M equals M, what's the direction? So which one is larger? M2 is much greater than M1. Okay, So let's just look at this before we do anything. So if M2 is much greater than M1, the M1 is essentially negligible here. Okay. In the denominator, it's essentially negligible. And so we've got an approximation M1, M2 over M2. And then the M2's cancel, so that's approximately equal to M1. So if you have a much smaller mass, the reduced mass is just the mass of that smaller mass. Okay. And then you can say, well, this one is going to be orbiting the large central body, and it's pretty much, yeah, it's pretty simple in that way. Now, this is much more general though, so suppose you have equal masses. So here was M2 much greater than M1. What if they're equal? Okay. If they're equal, then it's M squared over 2M, and the reduced mass is much different than the original mass of each one. Okay. So if M1 equals M2, then the reduced mass is equal to M squared over 2M equal to M over 2. So there are a couple limiting cases of interest. Okay. Interesting story about the reduced mass. It was also used, or it has to be used in the original hydrogen atom problem. Okay. Say the Schrödinger equation for the hydrogen atom, you've got a proton and an electron, and the proton is much more massive than the electron, but you can't just say the electron's, in a fixed proton orbit, but rather you have to use the reduced mass, and those couple percent difference show up in the data. Okay, so let's erase all of this. We're left with this expression here. Next thing we're gonna have to work on is the picture on the left here. So let's see, we'll put this up at the top of the board as what we've accomplished so far. And what we have now is M, R, it's a derivative, it's a central force problem, but this M is in terms of the two masses, so it's really a two-body problem, and as I had said before, we've reduced it to a one-body problem, formally. Yeah, but we're not quite done with this. We're not quite ready to just charge ahead with this now. So what about the individual motions? After we're done solving this problem, we would actually have to go back and say, well, what's M1 doing and what's M2 doing individually? And in order to talk about that, I'm going to go ahead and put a center of mass here. I'll just draw the star. Center of mass, that's what I like to do. So the center of mass of these 2 point masses is located somewhere in between them. Okay. And what we can do is let the center of mass be the origin. Let the origin of our coordinates be located at the center of mass. Okay. So we're going to take that as a new origin, and I'm still going to call these points R1 and R2. I could give them a new subscript, I'm not going to do that. So now, you could say, you guys know the definition of the center of mass. R center of mass equals M1 R1 plus M2 R2 divided by M1 plus M2. So what we're requiring now is that the numerator of this expression vanish. That's what it means for the origin to be at the center of mass. Okay, if we just let the numerator be equal to 0, it would be our origin. So, and M1 R1 plus M2 R2 is equal to 0. At the same time, All right, with R is equal to R1 minus R2. So we have two equations and we can express R1 and R2 in terms of this difference vector. So now express R1, R2 in terms of vector R. And that's done, no problem at all. It's going to save Newton's law up there. So we have, well, I guess I got to write it down after all. 1 R2, M1 R1 plus M2 R2 is equal to 0. So I can say M1, and I'll plug in the R1 from up here, R plus R2 plus M2 R2 is equal to 0. Then I have M1R plus M1 plus M2 R2 is equal to 0. And now you see I have R sub 2 is equal to minus M1R, M1 plus M2. And if you do the algebra, you'll see that R1 is equal to M2R over M1 plus M2. And in fact, you know R1 is going to be opposing R sub 2, so it doesn't have the minus sign, and then all I've done is replace the 2's with 1's. Okay. Yeah, so let's make sure we see that this makes sense. This has to make sense before we move on. So standing over here, we can see that R sub 2 is opposing the direction of R. So R is pointing at M1, R sub 2 is pointing there. So if I have different colors, I'm not going to do that. So I'll just do that. So there's our R sub 2, and there's our R sub 1. If we take the center of mass as the origin, no big deal. Okay, so now we actually have, you could say, the full system here. We're going to work on this alone, and these expressions are in the background. We can use them later when we need them. Namely, the definition of the reduced mass. This is now the reduced mass. And then the relation of these particle positions to this difference vector that we're using in our work. So yeah, this with these as conditions, and then we're ready to go. Okay, I'm going to say a little bit about two bodies and central forces, and maybe I have an interesting little homework assignment for you guys. Just to see what this whole center of mass business looks like. So let's call this homework center of mass and reduced mass. Okay, the center of mass and the reduced mass. The first example is the Earth Moon system. Our Earth, our Moon. So what I want you to do is, you're going to look up some numbers for this, okay? You're going to look up some numbers, put the origin in the center of the Earth, Moon's out here, okay? Distance from the center of the Earth to the center of the Moon. You look that up, you'll find it's approximately 60 Earth radii. That's kind of an important, interesting relation. That it's approximately 60, okay? And the question is, if that's the origin, where is the center of mass? So I'm going to say Earth, Moon, center of mass. You'll find that it's somewhere inside the Earth, so that the Earth-Moon system revolves around the center of mass, which is actually inside the Earth. Okay, so we want to do the Earth-Moon center of mass and then calculate the reduced mass. What's the center? Where's the center of mass of the Earth? Make a little drawing there, and then when you find the number, you can relate it to all these numbers here. The Earth's radius is 6,400 kilometers or something, so the center of mass should be less than that inside the Earth. Good, so we'll do that for the Earth-Moon. That's one of your problems. And then we want to also do it for the Sun and the Earth. Right, and that reduced mass we're talking about for the Moon, we'll see how much smaller it is than the lunar mass. The Sun-Earth system, again, if it were just the Sun and the Earth, nobody else in the solar system, where is the center of mass in the sense of this picture here, and what's the reduced mass? Reduced. Okay. And finally, we'll do the Sun and Jupiter. So your third problem, we'll do the Sun and Jupiter. And you can leave some space in your notes because those will be interesting little factoids of where those centers of mass are with regards to each of those systems. And for that, you look up some of those numbers in your Physics 4A book or elsewhere where you find those kind of numbers. There's usually a chart in the chapter on orbital mechanics. Okay, so that's just fun to do and of interest, and give us an idea of what this all means here that we've gone to. Okay. Yeah, next then, having done that, we're ready to talk about this equation and really pick up where we left off. Okay. We had been talking about this form of the problem, but we've reduced the two-body problem to a one-body problem now, and this is the one we're going to use. So I can erase everything and then remind us what we have learned so far. So now we're back to the same formal problem we had before. So here we go. M So what had we learned so far? We had learned that there is a potential energy minus we have potential energy. We have learned that L equals, let's see, R cross and R dot is a constant. Therefore, we knew we could use the plane polar coordinates. Polar coordinates, and we were then able to express the conserved energy that you have when you have a potential energy and the conserved angular momentum in terms of the plane polar coordinates. So then we were in the plane x, y. Our point is moving around in terms of the magnitude r and the angle phi. And those are both functions of time now. So what we hit upon was for the angular momentum, that was our one conserved quantity. And this is our one differential equation. Then the energy equation, we had already made a replacement with the phi dot. So we had for the energy a half m r dot squared plus L squared over 2mr squared plus u of r is equal to E. And that was also constant. Those were our two differential equations. But this one, we had already inserted this expression up here, so this had been reduced to a one-dimensional problem. It just has r here, it has r there, r dot. So that's why you could define this effective potential. It just means it looks like a one-dimensional problem. This still comes from the original kinetic energy, but that doesn't matter. Okay? Effectively, this is a one-dimensional problem, and if you can solve it, then you can go up into this expression and get your second dimension. Good, so that's how far we've gotten. We even have done a little bit of work on this. And before we get to the Kepler problem proper, we're still going to work with this in its general sense. Yeah, so the next thing we'll do, we've already spent some time analyzing effective potentials. We've learned that your effective potential can have, say, a form like this. The local minimum, U effective. The local minimum corresponds to a circular orbit, and that corresponds to a minimal energy. If you're at a higher energy, you have minimal and maximal values of the R, which means your orbit's no longer circular, but it takes place between two circles. So I have drawn something like this, R min, R max, and that R min. Okay. So now what do we do with an expression like this? We'll simplify it or make it a little more compact by writing 1/2 mr dot squared plus u effective of r equals E. And then we'll go ahead and say, well, we can start doing a quadrature on this. We can start separating variables. So that's our next step. Take this thing here, separation of variables. And we've done this before, so we've got our dr over dt is equal to 2 over m E minus u effective r square root plus minus. And if you were looking for the t dependence, you could say t is equal to integral dr prime divided by 2 over m E minus u effective r prime. We'd have the square root there. Okay. And you'd say it's r, so up to r. Everything would be prime. Yeah, it's good. So yeah, that would be as far as you could go in general. And then if you could actually solve this, then you could have, explicitly, if you knew the name of the function here, then you could have r of t. You can invert it. Same way we did the harmonic oscillator, for instance. Okay. Yeah. What did I do with the plus or minus here? It still exists. Okay. And yeah. And on the other hand, if I were still okay. So we'll just check that off. Victory. Okay, so what else can we do here? What I'm going to do is go ahead and write the same thing down in terms of just dt. So dt is equal to dr 2 over m E minus u effective of r. Keep my plus minus here. So there's our separation of variables. And we're going to use this one here, namely m r squared d phi dt is equal to L. So if we want to just do a quick and dirty substitution, we can just say dt is equal to mr squared over L d phi. And that, in fact, is what I'm going to do. So I'll make that substitution. I'll have mr squared over L d phi is equal to this whole thing. And what I'm going to do is solve for d phi. So that's a way to get this next integration. So I have this is equal to what's above here. And let's solve for d phi and see what comes out. That's just the substitution. So now we would have d phi equals, we're still going to have a plus minus. L over mr squared dr, all divided by our denominator here, 2 over m e minus u effective of r. Got the plus minus, and I'm going to I'm going to erase this. So this is the basis of our solution for the trajectory. Okay. The time has been eliminated. We're going to use this to obtain phi of r. Phi of r, or r of phi, which is to say the trajectory. Before we do this, here, let's close that off. Before we do this for the Newton potential, there is a little bit of general information we can get from this here. In terms of, so next, in terms of just the general information about the trajectory that this expression gives us, define delta phi is going to be the integral of this expression here, plus minus r min to r max, which were defined, remember, which we had studied. So it'd be mr squared dr divided by this whole square root expression, 2 over m e minus u effective of r. Got the plus minus in here. Yeah, so this delta phi is going to give us the angle equals, I could say, the angle swept out between r min and r max. So that refers to that picture I had been drawing with the 2 circles. So let's go ahead and draw that picture again with the 2 circles, concentric circles. One is the minimum, one's the maximum. And you can see now, if this expression here, don't worry about it, it is what it is, okay? This expression, if you start at r min here, and your trajectory takes you out to here, then you've swept out this much angle. So this is this delta phi. We're going to encounter this later again in a slightly different form. So that's that angle swept out. There it is. Now what's the meaning of the plus and the minus sign? Well, the plus sign is for increasing r, and the minus sign is for decreasing r. And what this result tells us is that this trajectory is symmetric in that sense. So as we go from r min to r max, we get a certain trajectory. If we go from r max back to r min, we're sweeping out exactly the same amount of angle, okay? Because it's the same expression here, it's just with the minus sign. So it's sweeping out the same angle. So I could write here the result is that the same angle is swept out. Same angle swept out. Swept out. R min to R max and R max to R min. Max to R min. Okay, so that's what the result is of this little insight. Yeah, I'm going to erase this, and then we can go to work on this expression here. Okay, we could actually erase the entire board and get a little more room for us. I don't think we need this anymore. Okay, so let's go ahead and clear things up. I think we can talk about the Kepler problem. Let's see about this. Yeah. Enough general stuff here. Now we have to get to the concrete case that we've all been waiting for. We want the Kepler problem, namely the Newton potential. So we call this Kepler problem. Yeah, and we're just going to use this formalism that we've developed. We have everything in front of us. So let's go back to what the Kepler problem is. Here, U of R is equal to, well, let's start with the force. Of course, that's Newton's law of gravity. F of R is equal to minus alpha over R squared. And I'm pretty sure this was a homework, right? The homework, namely, to integrate this up and get minus alpha over R. So for the Kepler problem, that is our potential energy. And next, we want to study the effective potential. And that is L squared over 2mr squared minus alpha over R. So this one is really interesting, needs some discussion. Okay. Namely, we have to graph this thing and appreciate it. L squared over 2mr squared minus alpha over R. And since I'm going to want this expression, I will clear up this part of the board. And that's enough to get this very typical result. Actually, this graph we want to be pretty big. I think this will be big enough. We want to have enough room on this one. So I'll block out this amount of board just for the effective potential for the Newton potential. Okay. So we've done these a few times now. We know that L squared over 2mr squared is always coming out from here. But yeah, the minus alpha over R is coming up from here. And what do? Okay, they both have diverging properties as R goes to 0, and they both vanish as R goes to infinity. But then you can say, which one wins? And for, better L there maybe? For small r, the 1 over r squared dominates for small r. So our potential is coming down from here. For large R, the 1 over R dominates, which means this one with the minus sign is going to dominate, and we're going to approach R from negative, from the negative side, and this is a wonderful picture. Okay, I just gave the argument, now I got to draw it all with one swoop. Okay, try to match that up. Now, so you come down here where the small r dominates, you reach negative values, and then you approach this asymptotically. So there's this stereotypical look. I feel like doing a better one. Let's see. You gotta have this in your wrist. Here we go, once more. Maybe that's better. Okay, so goes to infinity here, vanishes as we approach infinity on this side here. 1 over r. Yeah, and this has all the interesting features. First of all, r sub 0, that's our circular orbit. And there's the value, I'll call it e sub 0. What next? R sub 0, e sub 0. Okay, how about an energy e sub 1? Then we have a minimum right there and a maximum radius. And you'll see that they're not symmetric about the circular orbit value. Okay. So there's the R min and the R max. And this is as we discussed before. That means that the value of R is going to oscillate between its minimum value and its maximum value as the orbit takes place. It's going to go from minimum to maximum. Again, what we're talking about in this picture. But here's a new feature. What about e sub 2? So I have e sub 0, circular orbit, e sub 1 we just talked about. What about e sub 2? E sub 2. Above the axis here, these are negative energies, this one's a positive energy. The positive energy has a point of closest approach, but then it goes out to infinity. So that is an example of the Kepler problem where a particle comes out from infinity and goes back to infinity. Those are the hyperbolic orbits. If the astronomers can take the parameters of an orbit and see that it's hyperbolic around our sun, then they know that orbit, that object came from another solar system, came from outside of our solar system. Remember, we had one of those. It was in the news, Oumuamua or something like that. Okay. Should have chased it down and seen what was going on. But yeah, that's what was going on there. They had some orbital parameters that told them that it was a hyperbolic orbit. It was not from our solar system. Talking about our sun, our solar system would be all of these bound orbits here with the negative energies. So that's the difference. Negative energies, bounded states, positive energies, unbounded. Okay. So yeah, the discussion of the effective potential for the Kepler problem is pretty interesting, right? Pretty rich. What next? What's next is how long are we going to go today? Well, we're going to go a little longer for good measure, because what we want to do next, having done this, well, how about I put a little homework problem on this thing. So what you want to do is analyze this thing, find R0. You know, in other words, you do your first derivative criterion here and find an expression for R sub 0 for this Kepler problem right here. Remember, this is for a given value of the energy and in particular, a given value of the angular momentum. Okay. given value of the angular momentum, so in the effective potential graph, the angular momentum is always constant, and we're looking at different values of the energy. So find R0 and E0 in terms of these other parameters. Just to say we did something here. Okay. So our next step, and we actually do have time, I'm going to set this up and dump the whole problem into your lap, because we're really at the point where we can integrate this up and get R of phi. And I'll set it up and then we'll get the culmination of it after the spring break. So yeah, what we're going to do is integrate this thing. So let's go ahead and erase this and plug in what we have for the Kepler problem. Remember, this was still general. So phi equals plus minus integral, and let's just go ahead and write this out, L over m r squared dr. We've got a 2 over m E minus, but there's our effective potential. So E minus this negative, so we'll have alpha over R. So we'll have minus that, so we'll have plus alpha over R minus L squared over 2mr squared. Close parentheses. Square root. Yeah, that integral looks like a bear. We could put the R primes here and just go here from R. And what we're trying to find is phi of R, and we want to invert it and get R of phi. Yeah, I'm going to put that as a homework problem and then guide you through it. But this is a problem where I want everyone to have done it. I want everyone to have done this integral because it's a famous result. Okay, by doing every step here and doing this integral, then we can claim to have truly done the Kepler problem. Everybody, and not just seen it in the book. So yeah, we want to do this integral, and there are some simplifications according to taste. And there are different substitutions. You could actually go to a fancy integral table and just plug everything in under various conditions. Remember, the energy is going to be, we're going to do the energy for negative energy. But you can also do a couple of substitutions to make it simpler. Okay. So let's see what we got going here. Oh, and I'll even tell you right now, to break the suspense, it's going to turn into an inverse cosine. You have to do a couple of transformations. You can get this into an inverse cosine, and then you can reverse the transformations. So homework, just to have said it now, right? And then we have a few minutes to play around with this. Homework, integrate to, integrate and invert the result, and invert the result to obtain R equals P over 1 plus E cosine phi. This is the famous expression for the conic sections in plane polar coordinates. P and E are constants. They're constants with all of these parameters from the Kepler problem built in. So they're not that pretty, but this is a clean result. And it's a multi-step project to get from here to here. That's why I just wanted to put this up on the board. One thing you can actually see is that when E is equal to 0, you're going to have the circular orbits. Note that E equals 0 is the circular orbit. So you can actually go to your effective potential graph, calculate the circular orbit, which in fact is something I told you to do, and you would be able to figure out what this letter P has to be. It's going to come out of this calculation, but you can say that'll be a check on its expression. This will be the eccentricity of the orbit. And when it's equal to 0, then the orbit's circular, and when it's not equal to 0, it's either elliptical, or it can also be hyperbolic. Ellipse or a hyperbola. Okay, but how will we tackle this integration here? Now I've gone for about 50 minutes, and I could just leave us all in suspense, or I could do a minute or two more. I'll do a minute or two more. I'm going to erase the left side here and just show you what happens. Yeah, there are substitutions. So we'll name this thing star as always. And the first step is let U equal 1 divided by R. Then we'll have a du is equal to -1 over R squared dr. And when we go into this integral, we get now phi is equal to, we'll still have plus minus. I'll pull the L over M out front. L over M over root 2 over M. I wouldn't say that's that brilliant, but 2 over M integral. Yeah, the thing is we want to get rid of this thing. So we have the minus sign, the plus minus minus plus. No, we're going to get that over M. So dr over R squared is equal to du. So we've got a du. And then we have, pull the 2 out. We've got root E plus alpha U minus L squared over 2m U squared. Okay. And in fact, don't worry about the boundaries now because you're going to reverse all the substitutions. Okay, so there's a couple of things to do here. In fact, if we flip this and take it in there, we can cancel that L squared over 2m. And then we'll have du square root of something minus something times u minus u squared. Okay. So we can end up with e equals plus minus integral. Let's see if that works. So the 2 over m and the m over. Yeah. So here's what I'm going to write. You can have a du, and then you can have a root a minus bu, like get rid of the plus, sorry, minus u squared. Okay. The point is here, we just have this form. I'm running over, but you get something of this form and you're just 1.5, 2 steps away from an inverse cosine. Okay. Very close to an inverse cosine. You do a complete the square trick and you simplify this a bit more. I'll show you what you're going to end up with since you have all this stuff here. And it's easier just to sit down and crank through it on your own page. You're going to end up with eventually phi equals integral dw over root 1 minus w squared. Got a plus minus there. So at least that's the way I do it. I do a couple more substitutions, do a complete square trick down here. I end up with something of this form. Well, literally with this form, with the appropriately defined w. You know, I did a u, 1 over r to u, and I do something over to w. Get my inverse cosine, and then I reverse the transformations and make my way back. And finally, I'll get the 1 over r with a bunch of baggage here, and we'll be on our way. Okay. So anyway, we're going to pick this up again after spring break. Just wanted to take it a few steps because everyone's going to do this calculation. And, you know, some of you may do it by the time spring break's over. Nothing better to do during spring break, right? That'll be fun. So that is what we had to do today. We're kind of in the middle of the calculation. We know where we're headed. We're at the polar form of the conic sections. And yes, this was the 7th video lecture, the last one before spring break. And after spring break, we have a Monday and a Wednesday to get these things clarified and clarify all the exam taking issues, which will be on that following Friday. So everybody enjoy their spring break and see you later. See you next time. Okay, good. Ready?